Hello dear students, you're watching the channel Learn to Earn for Life. In this video, I will discuss the different sequence networks of power system elements. Before I discuss further about the sequence networks, I will just recall about the past sessions we have studied. The three-phase unbalanced phasors are resolved into three balanced phasor systems which are called as symmetrical components. You also know that in symmetrical systems, the currents of one sequence produces the voltage drops of the same sequence only. The power system components, namely the transmission lines, transformers, synchronous machines, are symmetrical in nature. A fault occurring on the power system usually renders the system unbalanced. However, using symmetrical components, each element can be represented by three distinct balanced decoupled networks on a single phase basis. This makes the analysis simpler. In this video, you will be studying about the equivalent circuits presented by the power system elements to the flow of positive, negative and zero sequence currents. Let me start with the synchronous impedances and networks of a synchronous generator.
Consider the three-phase equivalent circuit of a synchronous generator as shown in figure. The neutral of the generator is grounded through a reactor of impedance Zn. When the generator is delivering a balanced load or under symmetrical fault conditions, the neutral current is zero. But when the generator is delivering an unbalanced load or during the unsymmetrical fault conditions, the neutral current will flow from the ground to the neutral point via Zn. Let EA, EB, EC be the induced EMFs and IA, IB and IC are the currents flowing in the lines when the fault is taking place at the terminals of synchronous machine. Since a synchronous machine is designed with symmetrical windings, it induces EMFs of positive sequence voltages only. Here, this figure shows the positive sequence model of the synchronous machine, where Zn does not appearing in this model, as In is equals to 0 for the positive sequence currents. Let EA1, EB1 and EC1 be the positive sequence generated voltages and Z1 be the positive sequence impedance. Because of the balanced and symmetrical nature of the system, we can reduce this three-phase model of a synchronous generator to a single-phase model. Here, this single-phase model can be drawn with respect to phase A, using the notation E for the generated voltage and V for the terminal voltage. The system voltage that holds good for the positive sequence network is VA1 is equals to EA1 minus IA1 into Z1. This is the system equation for the positive sequence network of a synchronous generator. The negative sequence network models of a synchronous generator on a three-phase basis as well as on a single-phase basis is shown in this figures. The negative sequence induced voltages are not present in the equivalent circuits as they are not generated in the synchronous machine. However, due to the fault or an unbalanced load, the negative sequence currents can flow in the machine, which is shown here. Since the negative sequence currents do not flow in the neutral impedance does not appear in the negative sequence model of a synchronous machine. Here, the system equation that holds good for the negative sequence network is VA2 is equals to minus IA2 into Z2, which is written based on this single phase network model of a synchronous machine. Let us go through the zero sequence network models of the synchronous generator, that are ZSN of the synchronous generators. Here there are three possible cases for drawing the ZSN of the synchronous generator. The first case is when the neutral is present, that is the reactor Zn is connected to the neutral point of the synchronous generator and the ground. This is the three-phase model of that network, and this is the single phase model of the network when the neutral point is connected, or when the reactor is connected to neutral point. We can observe here very carefully, in a three-phase model the reactor is Zn, but while replacing onto the single phase model it will become 3Zn. The current flowing here is 3I0, but on single phase basis we need to mention it as I0. Hence the voltage drop here will be 3I0 Zn, and also the voltage drop here will be 3I0 Zn, will be maintained same in three phase model as well as single phase model. Let us go through the second case when the neutral is grounded via solid line. You can observe here, and this is the three phase model. The equivalent single phase model will be drawn here. You can observe very clearly that with respect to the neutral point and the reference, a solid line has been joined here. This is short circuited. Let us go through the third case where the neutral point is ungrounded. There will not be any reactor is used here in third case. So the equivalent single phase model can be drawn like this. With respect to the neutral point and the reference line, here it will be open circuited. You need to keep open. So this is the equivalent circuit on a single phase basis. So what we came to know, there are three possible cases. The first case is when the neutral is connected. The second case is a solid line neutral connection. The third case is when the neutral is not connected to ground, or it is an ungrounded neutral. There are three possible ways. The system equation that holds good, VA naught is equals to minus IA naught into Z naught. So this is the system equation. Let me summarize the different sequence networks of the synchronous generator on single phase basis very briefly. Let me go through the positive sequence network. Here it can be drawn as a reactor in series with EMF source with respect to reference. Here this is Z1 and this is EMF source EA1. The negative sequence network on single phase basis can be drawn as a simple reactor. Here there will not be any EMF source. This can be drawn with respect to reference. Here this reactor can be represented as Z2. Let me go through the ZSN or the zero sequence networks on single phase basis. The first case when the neutral point is grounded via reactor Zn. So we can draw a reactor of ZZ0 and a reference point. Here with respect to neutral point I can add a reactor of 3Zn. The second possible case is a solid line grounding of the neutral point. Here this can be drawn as a reactor of Z0 with respect to reference point, and this neutral point will be solidly short circuited to the reference point. The third case is ungrounded neutral or ungrounded star. Here simply a reactor Z0 can be drawn with respect to reference point, and this neutral point will be just kept open. Let us go through the sequence networks of the transmission lines. Here the first figure is the positive sequence network on single phase basis. The second figure is the negative sequence network of a transmission line on single phase basis, and the third figure is the zero sequence network of a transmission line on single phase basis. We can clearly observe that all the three sequence networks are similar in nature. One more thing is the positive sequence impedance of the transmission line is same as the negative sequence impedance of the transmission line. Let us go through the sequence networks of the transformer. This is the positive sequence network of a transformer on single phase basis, and this is the negative sequence network of a transformer on single phase basis. We can clearly observe that both the networks looks similar, as well as the positive sequence impedance and the negative sequence impedance are equal. Let us draw the zero sequence networks of the transformer based on static switch combination. This is the static switch combination shown. We need to draw this first while drawing the ZSN of a transformer. Initially we will be drawing this, which is having a primary series switch and a secondary series switch, a primary shunt switch and a secondary shunt switch. Then what is the rule to close these switches? There are two possible ways of closing these switches based on the winding connections. When the connection of the primary or secondary is either primary or secondary is star grounded, it means it may be a solid line star ground or it may be a reactor grounded. So if it is a star grounded, a particular side series switch will be closed. If the primary winding is star grounded, we need to close the primary series switch, or if the secondary winding is star grounded, we need to close the secondary series switch. Otherwise, if it is not a star grounded, keep it open only. As earlier it was open, we need to keep it open only. Now, if the connection is delta connection, if we find the primary winding as a delta connection, we need to close the primary shunt switch. Or if the secondary winding is delta connection, we need to close the secondary shunt switch. If there is no delta connection, means we need to keep it open only. As it was earlier open, we need to keep it open only. So this is the static switch combination or the rule we need to follow. Based on this, we can draw the ZSN or the zero sequence network for the various combinations of the transformer windings. Thank you for watching the video.